Hello everyone, my name is Meng Xiang, and my professor is Yan. I'm from the University of Aizu. The topic I report today is chaotic evolution using deterministic crowding method for multimodal optimization. This is my report outline today. I will discuss it from the following directions. First is research background. The second is algorithm. The third is experimental result. The last is conclusions. Let's look at the first part, research background. This is my first part outline. The first research background I want to introduce is chaos. Chaos has unique properties as follows: randomly, ergodicity, regularity, and sensitivity. Especially the ergodicity characteristics of chaos. To avoid falling into local minima during the search process. The application of chaos is also very extensive. For example, cryptography, meteorology, medicine. The second research context is niche. The essence of niching is the fitness of individuals in a population is adjusted by a sharing function that reflects the similarity between individuals. This is the niche method development. I will focus on DC algorithm. DC is a niche method that develops the crowding method. DC implicitly mentions multiple classes by replacing parent individuals with similar individuals. The advantage of DC is no niche radius and additional control parameters required. Niching is widely used in both academic and real life. Research background at the end of the first part is the multimodal optimization problem. Multimodal optimization problem refers to the maximization problem with multiple maxima in a solution space. The earliest study was presented in 1978. The right picture is an example of multimodal function. Every year there is a computation for multimodal optimization problem, and the name of the computation is CEC. We also use multimodal optimization in our life. In the second part, I will introduce the algorithm. This is my second part outline. The first algorithm I will introduce is CE algorithm. CE algorithm based on logistic mapping. Logistic mapping is one-dimensional chaotic system. Look at this formula and picture. Research shows that when mu takes a value between 0 and 4 and x takes a value between 0 and 1, the logistic mapping works in a chaotic state, and outside this range, the generated sequence must converge to a certain value. Circle 2 is a description of some chaotic evolution algorithm parameters. The process of generating mutant from the initial population target through the chaotic operation of Formula 1 is defined as the chaotic system. CE algorithm advantage is the simulation of chaotic ergodic motion and the output distribution of a chaotic system guarantee CE convergence. The second algorithm I will introduce is DC algorithm. The DC algorithm can prevent accident individuals from being eliminated by the selection operation, and effectively speed up the convergence speed and performance. Let's see algorithm 1. Algorithm 1 is DC algorithm pseudocode. Select each repeat for generation. We select parent P1 and P2 randomly without replacement. Yield C1 and C2 by crossing P1 and P2. Apply mutation operation on C1 and C2. We can get yielding C1 prime and C2 prime. Compare the P and C prime values. Values with better fitness replace worse values. At the end of second part, I will discuss my own algorithm. The CEDC algorithm is based on the chaotic method of the CE algorithm and introduces the comparative principle of the DC algorithm. The D and CP parameters guaranteed in the CE system ensure that we can search for individuals chaotically and randomly. DC can ensure that the next generation of the population has a better fitness value and a larger interval between individuals than the previous generation. Let's see CEDC algorithm from work. The first step is initialization. The initial population is generated randomly among the parameter search space. The second step is mutation. For every two target vector, two chaotic vectors are generated by formula 3 and formula 4. The third step is selection, to decide whether a new chaotic vector should become a member of the next generation. The chaotic vector is compared with the initial vector by a deterministic crowding algorithm. I draw a flowchart according to the specific process of CEDC algorithm. Over many iterations, the good individuals will replace the bad ones. As mentioned above, our proposed CEDC algorithm is shown in algorithm 2. The algorithm 2 shows the CEDC algorithm pseudocode. In the third part, I will introduce the experiment. This is my third part outline. First, let me introduce my test functions. I use 9 well-known benchmark functions as my test function. These 7 functions are 1-dimensional to 3-dimensional functions. These 2 functions are 5-dimensional and 10-dimensional functions. I conduct 4 sets of experiments respectively: CE, CEDC, JADC algorithms. I use 3 performance evolution metrics to test the quality of the algorithm, which are peak ratio, max peak ratio, and runtime. The PR value can reflect the convergence ability and the optimization ability of the algorithm. MPR defines the ratio of the sum of fitness value of the obtained optimal divided by the sum of fitness value of the actual optimal. We calculated the running time of the algorithm for each optimization. In the first subsection, let's see peak ratio results. The higher the PR values, the stronger the convergence of the algorithm and the more peaks that can be found. In the second subsection, let's see max peak ratio results. The values shown in the table are the ratios of the optimal value found by the algorithm to the global optimal value of the function. MPR can be measured over time to see how a niching algorithm behaves in terms of niching, formation, acceleration. In the third subsection, let's see running time results. We count the running time of the full algorithm for each optimization of the initial population. In the last subsection, let's see peak number results. After one experiment, each algorithm finds the numbers of peaks of each test function. The figure shows the number of peaks found by the turn generation for F1 to F9. This picture shows F1 to F6 benchmark test result. This picture shows F7 to F9 test function result. In the first part of this report, I will do some discussions according to the experiment. This is my first part outline. The first subsection of the first part is peak ratio and peak number. The test function from F1 to F3, the difference between the four algorithms are small, and the most peaks can be found. In the F4 functions, the CEDC algorithm is optimal, which can find all the peaks. As for the F5 functions, the algorithm under CE theory can basically find all the peaks in 30 experiments, while the JA algorithm cannot find all the peaks. In the F6 function, CE algorithm and CEDC algorithm can find almost all the peaks, which are better than JA algorithm and JADC algorithm. As for the F7 to F9 functions, the full algorithm failed to find all the peaks, but we can see that the algorithms under the CE series significantly better than the traditional JA algorithm. Failure to find all peaks is mainly because the diversity of individuals in the fourth algorithms gradually disappears as the number of iterations increases, leading to parameter convergence. In contrast, the CEDC algorithm found the most peaks in the experiment, and the CE algorithm was second only the CEDC algorithm, much higher than the number of peaks found by JA and JADC. The second subsection of the first part is max value. In low and high dimensional functions, the CEDC algorithm is almost better than other algorithms. One of the advantages of the CEDC algorithm is that it doesn't need to consider the particle distribution problem of the initial population, which is perfectly solved by a chaotic search. The third subsection of the first part is runtime. In terms of average time, it can be seen from the table that running an experiment to test all the test functions. The time consuming of the JADC algorithm is much longer than the running time of CEDC. This is mainly because when a JA algorithm is solved to a certain range, it often leads to a large number of inactive redundant iterations. The calculation time is relatively long. The solution efficiency is reduced, and it is easy to measure promptly. The last part of this report, I will introduce my field work. Currently, algorithms like comparative experiments, so I will use more algorithms to compare with our algorithm. The second, I will try more about each method. The third, I will apply the CEDC algorithm to a multi-objective algorithm. This is my reference about this PPT. Thank you for your listening. Thank you very much.